So we're looking at the inverse of the exponential functions. And these are called logarithms. Logarithms. And I've got a way to relate logarithmic functions to exponential functions, and called it the loop-de-loop. We do to translate over. Did you guys call it that last year, the loop-de-loop?
I think so.
The loop. Okay. Well, it seemed like last year I think maybe it was the year before. Anyways, I've got a little activity on that too if we need more help on it. But it seemed like coming from the advanced subject, you guys, this was last year, knew this. So here's what we mean. Here's the loop. At least with the logarithm, let's look at number 8, the good one. So if you have a logarithm is really just a logarithmic expression is really just an exponent on a particular base. So as a matter of fact, when we look at the graph of the logarithmic function, it's just a graph of the exponents, which grow much slower than the exponential function raised to a power that grows really fast. So as a matter of fact, in statistics, sometimes what we'll do is do what's called a transformation, where we transform the data into basically into exponents. We're just graphing the logs, the logarithmic expressions, and so it makes it so it doesn't grow quite so fast. So looking at number 8 is a good one to start with, and then we'll go back to 7. But the loop goes like this. This is your base right here. It's log base A. And let's try to see if we can get this thing to work right here in just a minute. Okay, so the loop goes like this. So the base is A, the power is 5, and the argument or answer is 4. So you can take there, that's how the loop goes. The base is written as a subscript of the log. The power is what the logarithmic expression is equal to. That's why we call logarithmic expression a power or an exponent. Yeah. And then what's in the back? This is the back side of what we started with. Let's pass it back. So that's how we rewrite that. So in this case right here, here's an exponential equation. How could we change that into a logarithmic one? Well, the base here is the 1.2. Okay, so we'd write log. Oh, there it goes again. Thing is a little confused. All right, so it'd be log base 1.2 of the argument or answer m equals the power 3. So the 1.2 is a subscript, and m is at the same level as the logarithmic expression. So when it's not written here, when you don't see, for example, on this logarithmic expression, if you didn't see a little subscript here, that means base 10, if you don't see it. And then ln over here means log base e. I'll rewrite that for you. How would this one on 9 be rewritten here? We have log. From a literal sense, it's log base e of 9 equals b. Now, on your calculator, you won't see log, L-O-G, base e. You won't see that. They've abbreviated it. So you'll see instead of log base e, you'll just see it written ln of 9 equals b. Okay, and ln, or log base e, is used often in calculus and beyond. Okay. Mathematicians are lazy, so if we could write 2 less letters, we will. So ln of 9. And as a matter of fact, when we go to take logs of both sides, I don't know if you were told this last year, but we'll oftentimes use just ln of each side instead of log base 10. Unless the base happens to be 10. But we'll just change the base to log base e and go for it. So right here, in other words, working backwards, what I'm saying that this is equal to is log base e of 4 equals x. That's what this means. And so then if you apply your definition, it's e to the power of x equals 4. So we can change that logarithmic equation into an exponential equation. And then finally here, this is the one where there's an unwritten 10 right here. An unwritten 10. So this would be 10 to the 5th equals a. All right? So that's the translating from logarithmic to exponential and vice versa using the definition, using the loop. All right, it says find the exact value without a calculator. So we have some expressions here. On your calculator, you can go to a menu and go ahead and put in a different base. On the front face of your calculator, you'll notice there's log base 10 and ln right in that first column. You see it there in the first column. So you can evaluate these with the calculator. These we're going to do without a calculator. So here's how it works. You can think of each one of these expressions as equal to some unknown variable x, if you'd like. And then we're going to rewrite them. So this would be 2 to the x equals 16 if I rewrite it as an exponential equation. So from the last section, how did we solve something like this? We haven't learned about taking the log of each side yet. We're about to. But what did we do to solve for x? You know? Yes. Yep. It's 2 to the 4th. And then x equals 4. And so we're asking 2 to what power equals 16? You may even be able to solve that just by thinking about it. Okay, but that's the method of same bases. Number 13 here, we'd have 3 to the x equals 1 over 27 if we rewrite it using the definition. And so 1 over 27 would be the same as 1 over 3 to the 3rd. And 1 over 3 to the 3rd is the same as 3 to the negative 3rd. And so we would say, okay, x has to be negative 3. So what we're saying is that this expression is equal to negative 3. Or this one over here, we're saying log base 2 of 16 equals 4. What I'm doing is I'm finding the power that I would have to apply the base 2 to get 16. Or here I'm finding out what is the power I would have to apply base 3 to get 1 over 27. So that's what I mean when I say a logarithmic expression is an exponent. Okay, it's giving me the powers on the base of the log. Okay. Right here, this we would have square root of 2 to the x equals 4. We didn't see one like this in the previous section. But square root of 2 can be rewritten as 2 to what power? What is it? It's 1/2, yep. It's 1/2 power, yep. A square root of 2, this would be an x on here. Square root of 2 is the same as 2 to the 1/2. Cubed root of 2 would be 2 to the 1/3. And so those roots can be written as rational powers. So then I'd change my 4 to 2 squared. And then now that my bases match, I can set 1/2 x equal to 2. And so x would equal multiply each side by 2, x will equal 4. Number 15. What's the base on 15? Yeah, it's ln, so it's log base e. So this is e to what power equals square root of e. And if you need to, you could rewrite it. I mean, this is the same as log base e of the square root of e equals x. If you need to do that, go ahead and do it. Then you could see by the definition how to rewrite this as an exponential equation. E to the x equals square root of e. And square root of e is the same as e to the 1/2 power. Now the bases are the same. So x equals 1/2. So every one of these can be done without a calculator. This one right here, it's 5 to what power equals 1. This one you got to know your properties of logarithm. 5 to what power? Yeah, 0. So this is x equals 0. It's the only way to get that equal to 1. All right, to solve for x. So once again, we're going to rewrite these as exponential equations. This one would be x to the second equals 64. So x to the second equals 64. And this one we would solve by taking the plus or minus square root of each side, right? So x is going to equal plus or minus square root of 64. So x equals plus or minus 8 for that one. Now, we should talk about what the bases can be here. When we look at this, I don't think I've actually talked about the domain of this yet either. But the solution to this equation is plus or minus 8. Now, in terms of what makes sense for logarithms, is only the positive 8. Right? We're not going to talk about a base that's negative. So you end up with, remember talking about extraneous solutions? Okay, when we rewrite this, we create an extraneous solution. The extraneous solution is, let me move this down, x equals negative 8. So we're only going to list x equals 8 only. So we can have a base of 8. But when it comes to logarithms, our base is going to be a positive real number. Okay? Positive real number. All right. Next one. How would you rewrite 18? Using the definition. So 3 to the second equals 4x minus 7. Good. So 3 to the second is 9. So 16 equals 4x. X equals 4. And as we rewrite these, we really should check all of them. I failed to mention that, but we should check all of them for extraneous solutions. If I plug 4 in, am I okay? 4 times 4 is 16 minus 7. The domain of a logarithmic function, we should really write that down here. The domain of the function y equals log of x. Let's write this down, please. So y equals log of x. The domain, and this is our third domain restriction, we should add this, is x has to be strictly greater than 0. Okay? So x is strictly greater than 0. Remember, we have two domain restrictions we've talked about. With the rational function, the bottom cannot equal 0. With the square root function, what's under the square root has to be greater than or equal to 0. And so now this is a third one. If you have y equals log of x as your function, the domain should be x is greater than 0. This one right here, we have 5 squared equals x squared plus 4x plus 4. And so that's 25. I'm going to move the 25 over, so 0 equals x squared plus 4x. If I go 4 minus 25, I get minus 21. We're going to factor this thing. So you can think of factors here that will work. Factors of negative 21 that add to equal 4. 7 negative 3 plus 7x minus 3. So x equals negative 7 or x equals 3 are possible solutions. Will they both work? We need to check them. Negative 7 squared would be 49. Plus 4 times negative 7 is minus 28. 49 minus 28 is 21. Plus 4 is 25. So that does work. The negative 7 does work. It gives me a positive value there that I'm taking the logarithm of. And then x equals 3 would be 9 plus 12 plus 4, which is also 25. So both of those work. Just keep in mind here this little domain restriction on the logarithmic function. Yeah. Different base. We can look at that. Let me finish up solving these, and then we'll talk about the parent graph of y equals log of x, and we'll do that before we get into this problem right here, actually. All right. We should really do that now. Let's go ahead and do that now. Let's look at it. You ever get calculators handy? Before we get into using logs to solve each. All right, so there's our graph of the two. Also notice that the blue graph here, the exponential graph, and the red graph, the logarithmic graph, which keeps going down here, are inverses of each other. They are symmetric about the line y equals x. Okay, the line y equals x. If I were to type in a third graph, just y equals x right here, and then hit graph. I'll graph one, and I'll graph the other, not very quickly. And then you'll see that they are symmetric about the line y equals x. There's the line y equals x coming in. So there it is. That's what tells us that down here, this graphing calculator is lying to us. It's got to keep going down here, right? It's got to keep going to be able to be a reflection over y equals x. Okay. So, since exponential and logarithmic functions are inverses of each other, the method that we use for solving something like number 20 here is anytime you want to bring the variable power down, you take the ln of each side. So this would be ln of e to the 2x equals ln of 5. And what happens when you take ln of e? It is 1, yes. And so if you want to, you can move the 2x out in front, and then ln of e is 1, so that disappears. And then one more step here. So one more step. X equals ln of 5 divided by 2. All right. So you take the ln of each side. Ln of each side to solve for the variable power. 21. Before I take ln of each side, I have to get rid of any terms that you see in front of the base e. Okay. And so first thing I'm going to do is divide by 4. So I have e to the x plus 1 equals 5 over 4. Then I can take ln of each side. So it looks like this. ln of e to the x plus 1 equals ln of 5 over 4. And I can move the x plus 1 out in front of ln of e. The ln of e is equal to 1, so I have x plus 1 equals ln of 5 over 4. And then one more step. Subtract the 1 over. So the exact answer here is x equals ln 5 over 4 minus 1. So I have x equals ln of 5 over 4 minus 1. So subtract the 1 over. All right. So don't forget to divide first here. Okay, move that 4 over first. All right, any questions on that? Right, so psychologists sometimes use the function L of t equals a, 1 minus e to the negative kt to measure the amount L learned at time t. There's an equation to do that. The number a represents the amount to be learned, and the number k measures the rate of learning. Suppose that a student has an amount a of 200 vocabulary words to learn. The psychologist determines that the student learns 20 vocab words after 5 minutes. Determine the rate of learning k. So we're given here to determine the rate of learning k. A little bit here. What we're going to do is plug in the learning and the time. So the learning 20 will go in for L of t, and the time 5 will go in for t. Okay. And then the initial amount, A, is the 200 right here. So this is my T, this is my L, and the 200 is my A. So I have 20 equals 200, 1 minus e to the negative k times 5. And we have to solve that for k. So remember what I said about getting, you need to isolate e first. We've got to get e all by itself. So what's the first step I'm going to do algebraically in this one to get e by itself? Divide by 200, yes. So divide each side by 200. Hopefully I have enough space. So we're to write small on the bottom here to look better. You might just need to kind of do it all on the right there as you go down. So divide by 200. And so when I divide by 200, I get 0.1 equals 1 minus e to the negative 5k power. All right, still e is not isolated. What do I need to do next? Subtract 1 from each side. Subtract 1. So I end up with, when I subtract 1 from each side, I've got negative 0.9 equals negative e to the negative 5k. Still, e is not all by itself. It's not isolated yet. But I could divide each side by negative, yeah. Divide by negative 1, divide by negative 1. So now I have 0.9 equals e to the negative 5k. Now it's like problem number 20, right? E is now all by itself. There are no coefficients of e. There are no numbers being added or subtracted from that exponential expression. So I can take ln of each side. So ln of 0.9 equals ln of e to the negative 5k. And we've learned that ln of e to any power is just that power, right? So negative 5k on the right. This is ln of 0.9. And then the final step is going to be to divide by negative 5. So when I divide ln of 0.9 by negative 5, I got a value of k that is 0.0211. So as a percentage, as a percentage, that value k, that constant k, or rate of learning, k as a percentage would be what? 2.11% learning rate, yes. Okay, so that's k. So the rate k is 2.11%. Or 0.0211. You could just leave it as a value k. When I ask how many words you've learned after 10 minutes or 15 minutes, that type of thing, what are we doing when I ask for 10 minutes or 15 minutes? Plugging them in. So on B, it's L of 10 equals, it was 200 times 1 minus e to the, now I know my k value, right? E to the negative 0.0211, and then I'm going to replace k with 10 instead of 5. And then we would plug that into our calculator. Let me show you on one of these, and the next one I'll just give you the answer here. But on the calculator, here's what this will look like. Okay, so we'll type in 200, and then in parentheses, 1 minus second e to the negative 0.0211, and then in parentheses, times 10. And then make sure you get out of the power before you put your second parenthesis. If you're using the classic mode, that TI-83 plus, then you'll have to use parentheses around. It'll have E, and then it'll have a little caret, and you have to have parentheses around the entire power. And then hit enter, and you get about 38. So about 38 words a student would learn after 10 minutes. And then you do the same process for 15 minutes. I ended up with about 54 words. You won't do that calculation. Are you able to do it on the classic? You guys get that value? Okay. So 38 words, and then the next one was 54. So 38 words, 54 words. So trying to mathematically calculate how many words you would learn, if, of course, this model is a good one. 38 words. This is about 54 words. So you could do a mathematical calculation and figure out how long it's going to take you to learn all those vocabulary words. Unless your rate of learning happens to be different for your students. All right, then it says, how long does it take for the student to learn 180 words? Okay, well, that process, so this one was 38. So that's D. When I ask how long for 180 words, I'm asking you to go through this process again. Okay. You're going to replace 180, replace L of t with 180, and then we have equals 200, 1 minus e to the negative 0.0211. This time, I'm not solving for k, but I'm solving for t. But it's an equivalent process to what I did here. It doesn't matter if it's k or t that I'm solving for. They're both variable powers. So when you have variable powers, you're going to end up having to take the ln of each side or log base 10 of each side to solve. Just you have to get that in your mind. When there are variable powers, unless, of course, you can use the definition and use the method of same basis. Okay. So I divide each side by 200 here first. I'll run you through this here. So you get, and then I end up with 0.9. 1 minus e to the negative 0.0211t. Subtract the 1 over. I'm going to subtract the 1 over and also divide by negative 1 in the same step. Okay. So you end up with 0.1 equals e to the negative 0.0211t. And then we take ln of each side. So if I take ln of 0.1 equals ln of e to the negative 0.0211t, I end up with ln of 0.1 equals negative 0.0211t. 0.0211, yeah. That was the K value we got when we did part A. That's the rate of learning is about 0.0211 or 2.11%, yeah. And then divide by T. So ln of 0.1 divided by negative 0.0211. So what is the time it's going to take me to learn 180 out of the 200 words? According to this model, what do you get? Yeah. Okay, what is it? Okay. So on a calculator, here's what it's going to look like on a calculator. Okay, you type in ln, okay, ln of 0.1, and then divide it by negative 0.0211. Make sure all your you get about 109, yeah. So we'd have to probably round up, I guess.
Because you can't read 0.1.
Right, yeah, I think that's the idea. So we would need to round up in this case, and so t would be about 110 minutes. We could use squiggly equals here, about 110 minutes. That's about as difficult as the problems that I'm going to ask you to solve will get. There is a section in there of shifting the logarithmic functions. I was going to talk a little bit more about that. If you're struggling with that, we can work on that some more tomorrow. We have some work there. But make sure you do all the equation solving. You should be able to do all those. But there's like a whole matching section again. And I'm going to ask you the same thing you did. What's that? Matching section. Well, you have your calculators. Use your graphing calculator if you want to check them. All right.